Welcome to Physics 163, Chapter 24. At the end of this chapter, you should have a better understanding of light propagation through a medium, plane waves, rays, re-radiation and superposition, index of refraction, and refraction itself, reflection, Snell's law, a total internal reflection, and lenses and mirrors. Okay, to start off this podcast, I forgot to talk about resonance of an accelerating charges. During the re-radiation, the natural oscillating frequency of the charge is important. And so what I mean by this is that if the incoming radiation is close or equal to the natural frequency of the natural oscillation frequency of the charge, it will have much larger amplitudes or oscillate at larger amplitudes. If it's not close to that incoming radiation, then it has smaller amplitudes and won't re-radiate as much. Alright, let's talk about light propagation through a medium. Alright, so we need to talk about some wave fronts, and this is a picture of a wave front. We use circles to represent the crest of the wave, so that is one crest, and here's another crest. And this shows how the front of the waves propagate outwards from the source. When the radius of this circle that's propagating out gets large, then if you're up close to the circle, it appears that this is a planar surface, and we can treat these waves as plane waves. And these blue squares represent where we could treat them as plane waves. The last thing is we can treat electromagnetic radiation as traveling in straight lines, and we call these lines rays. These green arrows are representing a ray, what we refer to as a ray of light. And these rays will travel in straight lines. Alright, what does wave fronts look like? So here I have a source, and you can see the rays from the source. What would the waves fronts look like? They would look like this, and the gray is a different medium, and you can see what happens to these wave fronts as they enter another medium, and it looks quite different there, but this is how waves propagate outwards from the source. They radiate at 360 degrees. It's a spherical radiation. All we're looking at is a slice of that spherical radiation. So the big question is what happens to the radiation as it enters a medium. So what's going to happen here is the gray dots are charges in the medium, and these charges will be accelerated by the electromagnetic radiation that is hitting it. And so what happens is you have multiple radiating objects, and we have superposition going on. And if you remember, that's where when you have multiple waves in a medium, to get the total displacement of the medium, you add up each individual displacement caused by each ray. So the red dot shows you a point where two waves are intersecting, and this can happen at multiple points in this situation. So here, there, there is where you're going to have superposition taking place. The other thing is you definitely see the blue wave fronts. That's the initial radiation that hit it, and then each individual charge is re-radiating its energy, and you notice that it re-radiates in 360 degrees around it. So the incoming radiation is going to have to give up some of its energy to cause the other charges to radiate, and they will radiate in all directions. If the radiation is in the opposite direction of the incoming electromagnetic wave, then that's called reflection. If the re-radiation is in the same direction as the incoming radiation, we get superposition of both those types of radiation, and that's called transmitted radiation. It's transmitted in the medium or through the interface where the medium occurs. And so what happens in transparent media? Well, you get this re-radiation, but if the medium is transparent, you have this superposition that's going on. You have constructive, and you have destructive or constructive interference. Destructive is that the waves, when they come together, when you add up their displacement, they add up to 0, or less than the individual displacements by themselves. And if you have construction, they would add up to be bigger than the individual displacements of themselves. And so in a transparent medium, the re-radiation is always constructive. So that's why you can't see, you can see through transparent material. Let's talk about the index of refraction. You can definitely see here that the distance between the wavefronts when it's in the white medium is greater than that's in the gray medium. So definitely traveling at a different speed. These wave functions happen at individual time intervals, or they're separated by a period of time, t. So the way we define the index of refraction, it's the ratio of the speed of light in a vacuum to the speed of light in the medium itself, and you can see it travels slower in the medium itself, so it's always going to be less than the speed of light. So the index of refraction should always be greater than 1. Never less than 1. Alright, so when you look at this refraction, what's going on? Well, it's definitely going at a higher speed when it's in the white medium, and a slower speed in the brown medium here. And so we usually refer to this as a marching band approach. The marching band will move slower in mud than it does in, say, dry on asphalt. So if you happen, and this is what happens when the ray is perpendicular to the surface of the medium between them. Now, if you come in at an angle, it looks like the ray actually changes direction, and it will change the direction in refraction, especially if it comes in at an angle to the normal of the interface between the two mediums. Alright, again, okay, so now with reflection, the re-radiation is emitted back in the opposite direction of the incoming radiation. This makes the re-radiation, since the atom, or the charges that are radiating their energy they got for the incoming wave at 360 degrees, there's less energy going back in the original direction of the blue radiation here. So that tends to make it dimmer than the incoming radiation. This is reflection are much dimmer than the rays that are causing it. We like to be able to determine the angle at which the rays will bend as it enters a new medium. We call this idea Snell's law. The way we do this is we measure the angle of the incoming ray with the normal barrier between the two mediums, the white and the gray, and then we measure the angle the same way for the outgoing ray, and so we call this angle theta 1 and theta 2. Now what we're going to do here is, you see this triangle, D is the same for both triangles. Here on the opposite side of the triangle here, you have this distance right here, and that distance is equivalent to the velocity of the wave in the new medium, in medium 2, divided by the period. The period of these waves front should be the same, because the frequency does not change when the medium goes from one location to one medium to the other. What changes is the speed and the wavelength. Now here, the distance between the two wavefronts is v1 times the period t. So what we're going to do is we're going to calculate d for both triangles. For triangle 1, we get sine theta 1 is equal to this. For triangle 2, we get sine theta 2 is equal to this. The d's is equivalent, so I want to set them up to be equal to d, and then since d has to be equal, we're going to set these expressions equal to each other. You'll notice that we can cancel the t's, and we're left with this expression. Now what I'm going to do is plug in the definition for the index refraction here, and we're going to solve that definition for v1 and v2. So you would get v1 is c over n1 and v2 is c over n2. If we simplify this expression, we get this. The c's will cancel, and so we can take the reciprocal of this equation, and this last one down here, n1 times sine theta 1 equals n2 times sine theta 2. This is called Snell's law. And this allows us to determine if we have the incoming angle, we can determine the outgoing angle, and vice versa. A special case of Snell's law called total internal reflection. And you have your two mediums. This only happens when you go from a larger index refraction into a smaller index of refraction. And what happens is the transmitted or the outgoing ray gets bent perpendicular, or I should say parallel, to the interface between the two surfaces. If we do that, the angle theta 2 is 90 degrees. So the sine of 90 degrees is 1. So we get this expression. I can calculate the angle at which you would get total internal reflection by using this expression, and any angle equal to or larger than this, you will get total internal reflection. That means no electromagnetic radiation will be transmitted past this barrier. It is just reflected off of the barrier, and it would come off. We would apply the law of reflection, and this angle would be the reflected angle, and that would be equal to 60 degrees also, because the law of reflection is the angle of incidence equals the angle of reflection. Now, if we generate objects with different indexes of refractions, one of them is a prism, you can, and if you shine white light into it, the prism will create a rainbow. This happens because the index of refraction is dependent on the frequency of the electromagnetic radiation. So each wavelength, different color of light, or wavelength of electromagnetic radiation, electromagnetic radiation has a different wavelength, and that makes it have a different index of refraction, and that's why the prism separates the different colors of light, or same way as a rainbow. Where in a rainbow it's a water droplet that will refract the rays of light, or separate them so you can see the colors. Well, what we want to do is arrange this object, this glass prism, so that we can bend the rays of light into particular orientations to where maybe they're going to cross each other or diverge from each other. We have a converging relationship here because the incoming rays cross, they converge. And here we have a diverging relationship. The incoming rays will separate and get farther apart, so they diverge. And these are crude ways of generating lenses. If we're more sophisticated, I can generate what's called a converging lens, where all the light rays will converge at one point, or a diverging lens, where the light rays will diverge away from the optical axis. And a converging lens, they converge towards the axis of the lens. I should say, they get deflected towards the axis of the lens for a converging lens, and they get deflected away from the axis for a diverging lens. So in order to understand and make predictions about what the light rays will do when they enter the lens, we're going to use the small angle approximation. And using these triangles, the definition of tangent theta is sine theta over cosine theta. What we're going to do is use the small angle approximation. That's going to allow us to approximate theta as being a small number. That means that cosine theta will go to 1, because cosine of 0 is 1, so we're going to say theta is small, close to 0. That'll allow tangent theta to be sine theta. And we can even approximate it more. We can say tangent theta and sine theta are equivalent to theta because it's so small. When we do that, that allows us to approximate the hypotenuse of our triangles. And the red one is a right triangle, so it's basically, if it's to approximate x, is to be equivalent to r if theta is small. And the green triangle is an arc length. The opposite side of the triangle is not a straight line, it's curved. And this allows us to say that x is equivalent to r. And we're going to use these approximations in calculate lenses. So we want to figure out how much the lens is going to deflect the ray of light. And so we'll start with the converging lens, and the point at which the deflected ray intersects the axis of the lens is called the focal point. This happens when a ray comes in parallel to the axis before it gets to the lens, and it gets bent towards the axis, so it converges at one point. The distance between the lens and this point is called a focal length. So we have two rays here, one with an angle theta and the other one with angle theta. Using geometry, we know that this angle is also theta, and then this angle here would be 2 theta. So what we're going to do is approximate this triangle. We've got y here and f here. By definition, tangent theta should be y over f. And I do it for the larger triangle also. I'm going to use the small angle approximation. So tangent theta is equal to theta, and tangent of 2 theta is equal to 2 theta. And what does this tell us about the deflection angle? It tells us that the deflection angle has to be equivalent, or theta has to be equal to lambda y divided by f. That says if y is twice as large, then it should be deflected twice as much. Alright, so this works for all rays that are deflected by a thin lens. It does not matter that the incident angle of the incoming ray. Let's say we had these rays, and what we know is this ray comes in, it gets deflected, this angle of y divided by f. Well, I have a triangle here, and I know that if I sum up all the angles in the triangle, it should be 180 degrees. So what I'll have is 180 has to equal alpha plus beta plus this top angle right here. And so the top angle has to be equivalent to that. And then they have this straight line, the angle between this straight line here has to be 180 degrees. So I know that I would know this angle plus that angle has to be 180 degrees. When I set this up here, I get the 180 degrees angles cancel. We bring them, I move this over to this side. I have 180 minus 180, so it's 0. So we can solve this for this expression. The thing is, what is alpha and beta? What are they? Well, I'm going to use the small angle approximation for them too. So alpha would be y divided by d2, and beta would be y divided by d2. So alpha is y divided by d1. Sorry about that. Well, I got y's on both sides, so I can cancel that, and we come up with what's referred to as the thin lens formula, and this allows you to predict, if you know the location of the beginning ray, the beginning ray of light distance before the lens, and you know the lens's focal length, you can pick where it's going to intersect later on. So it gives you an algebraic way of detecting where our rays are going to intersect the axis. So this is an example that you can tilt this triangle and it still works. We don't have to change our analysis just because we're tilting our system. So these rays can come in at any angle. So how do we have image formation? Well, you basically have to have a source that radiates its energy 360 degrees. And some of this energy has to hit the lens, and the lens will actually focus it to a particular point, and where that point is will be where the image is located. Now, the way a lens works, if the light travels from the source through the lens to the image, then that image is called real. And then I should type an image called a virtual image. You can see here the source starts here, but I don't see the rays after going through the lens converge. They do converge. What your eye will do, if it sees this light here, your brain will backtrack along that straight line until all these rays converge, and at this point right here, your eye will perceive an image. Now, since that's on the same side as the source of the radiation, that's called a virtual image. It's not working like it should be. The light rays should travel from the source towards the lens, through the lens. Since the light rays do not converge there, this image is called virtual. There is a difference between an image, a real image, and a real source. If you look at the real source, the light rays are coming out in 360 degrees. And an image, they're not radiated 360 degrees, they're only radiated in one particular direction, the direction away from the lens. Now, thin lenses are not perfect. Like I mentioned, the index of refraction depends on the frequency of the electromagnetic radiation. And so if you had two different frequencies of light, they will not converge at the same point. This is called an aberration. And as long as that's small, we're okay. If it gets a little larger, we see the image becomes fuzzy. So how do we create these image formations or estimate where they are? One way is if the light comes in parallel to the lens axis, then all light rays get bent through the focal point. And so that is the focal point of the lens. That's what we call a focal point. And it's on both sides. There would be another one on this side if its curvature is the same on both sides. Alright, a diagram way of predicting the way where an image is going to be created is called ray tracing. So I'm going to do a ray trace for converging lens. The green light is going to represent our lens at this point. The white line is our optical axis, or the axis of the lens. The red dots are going to represent the focal points. And I've tried to set this up to be the focal point to equal distance from the lens. And there's my source that's going to radiate the electromagnetic radiation. It's going to be a arrow, black arrow. So, and we usually call that the object. Alright, so how do we do a ray tracing? Well, we're going to pick a point on our object and draw straight rays and figure how they bend. So the first ray comes off our object and is parallel to the axis and hits the lens. That has to be bent through the focal point on the opposite side of the lens. Our second ray is going to come through the focal point on the near side of the lens. And since it entered through the focal point, it's going to get bent so it comes out parallel to the optical axis. And you see there's the two lines converge. And then a third line would be a line that goes through the center of the lens. And if that happens, the ray will not deviate in any way. And you can see that my drawing is not 100% accurate here because the lines are not intersecting all at the same point, but that's because I didn't draw this to exact scales and measurements. But it gives you an idea. Our image should be forming, at least the top of our arrow should be forming where these rays are intersecting. So I'm going to put it in there, and then you can do this for any point. I'm going to choose the bottom of the ray, or the arrow, black arrow, and do the same thing. The ray comes in parallel to the optical axis, hits the lens, gets bent through the focal point. The next ray goes through the focal point on the near side of the lens and gets bent out parallel, and they intersect at the tail of the gray arrow. The gray arrow is our image. Now, the way we describe these images is, since this is on the proper side of the lens, it goes from the source, the light rays go from the source to the lens, through the lens, and intersect on the opposite side of the lens. This is called a real image. It appears to be about the same size as the object, and it's inverted. It's upside down from the object. Well, if we change the position of the object, okay, before we change the position, we need to find the measurements here. D is the distance between the source and the lens. D1 is the distance between the source and the lens. D2 is the distance between the lens and our image. The focal length is the distance between the lens and the focal point on both sides. Now, if these are all positive, for converging lens, the focal lengths are always positive. D1 is positive if it's on the proper side of the lens as light travels, so the source goes, the light ray goes from the source, the black arrow, to the lens, through the lens to the image. If it does that, D1 is positive. If there's a real image or the image is on the opposite side of the lens as the source, D2 is positive. Okay, if D2 is on the same side as the source, D2 has to be negative. Alright, let's do another converging lens. Let's move the source closer to the focal point. And if we do the same thing, our same strategy, where are our objects going? Notice I'm only doing 2 rays for one point. You have to do a minimum of 2 rays to find them if they converge. But you can use all 3 if you want. And you definitely see that the object is inverted. It is definitely larger than before. And it's still a real image. Okay, diverging lens. So on a diverging lens, the focal lengths are negative. Alright? So if we do the same setup with the diverging lens, there's a little different strategy. So the ray comes in parallel. Now that has to get bent through the focal point, but it's not the focal point that would be on the opposite side of the lens. It's the one on the same side. So I draw a dotted line back to see. Dotted lines are going to be the virtual image lines that we use to trace back this. Your eye will trace it back and follow it straight back this way. Okay? And I've got it the best I can to keep it straight, almost to the focal point, but not exact. So that the next ray goes through the focal point on the opposite side of the lens, and then it would get bent. Sorry, it would get bent straight. You notice how these rays are not converging. So if we do the bottom, and then I backtrack this ray to here, you see they do the. You see that the rays converge on the source side of the lens. So I put my image there. I do it again for the bottom of the arrow. Same strategy, through the near focal point first, now through the far focal point, and it gets bent straight out, and then I have to backtrack. You see that they're not all intersecting at the same spot. That's because I haven't drawn my ray diagram, but you get the idea. You can see that the image shows up on the same side as the source. This is what we refer to as a virtual image. You can definitely see that none of the rays are converging on the proper side of the lens. Now, D1 is the distance between the source and the lens. D2 is the distance between the image and the lens, but that's on the wrong side. It's virtual, so this distance has to be a negative number. Okay, let's practice with a few problems. So this problem, the diver is underwater, shines his flashlight upward towards the surface at an angle of 29 degrees from the normal. At what angle does the light emerge from the water? Snell's law will allow us to calculate the angle theta you see here. So I apply Snell's law. In this case, N1 is the water, N2 is the air. Theta 1 is 29 degrees. So if you calculate for sine theta and take the inverse, you get an angle of 40.1 degrees. Now you can also calculate, you can draw ray diagrams or you can calculate the value. So in this problem you have a converging lens whose focal, in which an object is 15 centimeters away from the lens. D1 is 15 centimeters is positive. The lens has a focal length of 10 centimeters. They want to know where is the image located. It says where is the location image of the source. So we got to find D2. So we apply the thin lens equation, put in F and put in D1, and solve for D2. You should get 30 centimeters. I hope you enjoyed this podcast, and I hope you have a better understanding of the material.